Okay, today we're going to talk about Taylor series. And they're basically a mathematical idea that helps calculators function in general. Taylor series. Okay, but let's start the idea of what a Taylor series is. A Taylor series is basically an infinite sum of polynomial of a polynomial equation. So like an infinite sums of x squares, x to the cubes, all the way to the x to the infinities. It's an infinite sum of them. And basically, you're like wondering why would I want to sum, like why would I want to add up, get a function that you can add that has an infinite amount of terms in it? It's because those functions can actually be represented to be equal to another function that we can't really calculate in the real world. But we can using Taylor series, and that's how your calculator does it. Functions like cosine, e to the x, log, they're done using Taylor series, and they're done because of the approximations, but like to a really accurate degree. You're probably wondering now, like what is this kid talking about? It's a bunch of gibberish he's talking about. How can you approximate a function using polynomials? Let me explain it. So let's say we have a function on the xy plane, y equals f of x. Okay, so and let's say I choose a point. Let's choose a point, A. F of A. Okay, sweet. So you've done a lot of like linear approximations, so let's do that right now. If I want to approximate the function as a line, what would I do? So the first step is to find the slope, and let's say that f of x is a differentiable function. I forgot the specific name for it, but like there's a specific name for differentiable functions that are differentiable infinite amount of times. Basically means that no matter how much you differentiate it, it's always defined at a. So like no weird stuff, okay? Just a simple old function, basically. And let's find the linear approximation. Okay, well, we did this a lot of times, so let's get this out of the way. Let's see a linear approximation. Let's say the linear approximation of, let's call this y1 because this is our first approximation. So, you know what, let's call it g of x1 for approximation 1. Okay, this is the first approximation we're going to do. This is the first approximation we're going to do. And what we're going to do is, we're going to do this, we're going to take the linear approximation. So how do we do that? It's pretty simple. We're going to take the slope of the function at a, multiply it by x minus a, and then add f of a. If you're wondering how I got this, it's pretty simple. This is the Poinslow form, like Poinslow form as in y minus y1 equals m times x minus x1. Basically, it's the same thing. I just added y1 on that side, and that's f of a. M is the derivative at a, and x1 is just a. So that's g of x1 at linear, right? Linear approximation. Okay, let's say I want to add a second term, like make it more accurate. Let's say I want to do a quadratic approximation. So maybe it looks something like this. So obviously when you're first looking at this, it's actually more closely aligned with the function with more values than the linear approximation. So in order to do that, I gotta think of a function that has the same slope at that value, instantaneous slope at that value, and the same concavity, right? We're looking at the same exact concavity, the same slope, and the point is at the same. So we can basically going to expand the linear approximation formula. So what we can do is we can add another point right here. Add, say like I can do expand on Poinslow form equals m times x minus x1. But let's add like another thing, c for concavity at the point. and x minus x2. Or like, let's just say this is the x minus x1 actually, because it's the same point, right? Squared. And c is basically the concavity at that point. But keep in mind, since we're trying to make it as close to the function as possible, we're gonna actually divide by 2 over here. Because if we differentiate this twice, we want to make sure the 2 goes away, so we get the function back, right? Because if we don't have the 2 over here, we're going to be left with a function that has an unnecessary 2 when we differentiate this twice. Because this is an x squared term, so which is why we're dividing by 2, so that if we go back to from the concavity to the linear to the original function, there's no weird 2 stopping us and making it look weird. We want to get rid of the 2 by dividing by 2. So this is the added term. This is kind of like a quadratic approximation. Like this is the linear approximation. This is the quadratic approximation. So let's build our second function. G of x2 equals, well, obviously the same. The first part is the same. Plus f of a plus, okay, let's do this. What is the concavity at point A? That's simple. That's just the second derivative at point A. So we're going to do f double prime of a times x minus a squared, like right here, and then we're going to divide by 2. Okay. Now let's do another step. Let's do the cubic approximation. So it'll look like this. Oh, that's awkward. Ooh, like this. Now, obviously, you can see this is the gx1, gx2, gx3. This is actually a more accurate projection of the last two. So you know what? We should probably do the third one instead. If we're gonna do these 2 steps, we might as well go for the third. So let's do the third. Let's expand on point slope again. You're probably already seeing a pattern. So we're probably going to do this same thing. We're going to copy down y minus y1 equals all of this stuff right here. But we're going to add a third term. And this third term is going to be the, I think in physics you call it jerk. But basically how much is the rate of change of the rate of change of the rate of change is at that point. So let's just call it t for third derivative. I don't know, probably a bad idea to choose t. Let's choose sigma, because I'm so sigma. Okay, I don't know. And then we're gonna do the same thing, x minus x1 cubed, because this is the cube term. This is basically this is the cubic term, right? But this time we want to make sure that we differentiate it 3 times. We don't have any weird constants coming in our way. So we got to divide by 3 times 2. You're probably seeing a pattern there. So g of x to the third, gx3 is f, let's rewrite it. Let's put the derivatives in order this time. But the same thing, f triple prime of a times x minus a cubed over 3 times 2 times, this time I'm going to put a 1, so it makes a little more sense, so the pattern probably can become more obvious to you guys, plus f double prime a x minus a squared over 2 times 1 plus f prime of a times x minus a over 1 plus f of a, right? Because when you're doing this 1 is here, because obviously when you differentiate this, you're really multiplying by a 1. So, but it really doesn't appear. But for now, just observe the pattern. We're basically gonna pattern. So like, let's say I do this for infinite amount of terms. So keep on going, because as you can see, the more terms we add, the more accurate approximation. So let's find infinite amount of terms, because why not? Because you want to be the most accurate possible. So let's find g of x to the infinity. So like the infinite amount of terms of g of x. Okay, function's probably going to look like this because the pattern is holding true. Obviously, that function is going to like converge to the original function. Okay, well we know that. Maybe, okay, so now let's look at the pattern. We'll have f of a, and really we can say this is x to the a to the 0 over 1. Same thing, because x to the x minus a to the 0 is 1. What is 1 again? 1 is the same thing as 0 factorial. This is the same thing as 1 factorial. This is the same thing as 2 factorial. And this is the same thing as 3 factorial. And this is 0 over here, 0 over here. This is really the 0th derivative. So maybe if I want to find the infinite amount of terms, maybe I just add up all the whole integers from 0, positive integers, or like whole numbers up until infinity of this pattern. So like the say like we have the nth whole number, we want to multiply the nth derivative at a times x minus a to the nth power divided by n factorial. That's the pattern we're so far looking at. So let's do that. What that will look like is we're going to have the summation from n equals 0 to infinity, right? That's just the summation thing. You know, let me write this. I'm realizing that it's kind of like cluttered, so let me write this over here. So summation n equals 0 to infinity, because remember, this is all whole numbers, of f to the nth derivative of a, because we're taking the nth derivative every time, times x minus a to the nth power, because we're raising it to the nth power every term, and then we're dividing it by n factorial, because when we differentiate n times, we want to get rid of we want to get the original function back, so we're going to divide by n factorial. And look, this will equal f of x. That is the idea behind a Taylor series. You can basically, from infinity, this is infinity by the way, if it's pretty unobvious, but this is the idea. You can essentially add up a random infinite set of polynomials and you'll get a function that is usually never easy to compute. It could be, usually I'm talking about cosine, logarithms, all that stuff. So yeah, let me show you some examples of Taylor series that exist in the real world. So let's do 2. Okay, so like I said, 2 functions. Let's find some Taylor series. Now, this is not going to be as bad as you think, but let's do it. Okay, we have cosine. Now, for a Taylor series like we discussed, we're going to have to take an infinite amount of derivatives. You don't really need to do that. I don't think you'll even be like expected to do that. But what will be expected of you is to find patterns. Find patterns in the numbers that you compute, or most likely the derivatives you compute. So let me show you. Let's have fn, like the nth derivative of g of x this time, and the nth derivative at the value a we choose. Now I'm gonna introduce a new topic. If the a that we choose, like last time we were talking about centering the Taylor series around that a value, building each approximation from the a, if we build it from 0, it's called a Maclaurin series. Basically, a Maclaurin series is the Taylor series at 0. That's it. So let's in fact choose a to be 0, because you know what? 0 is a fancy number. 0 is a cool number. Indians invented 0. I mean, I should probably support my people, but yeah. So we're going to do that. Okay. So let's do the 0th derivative of cosine of x. That's just cosine of x. 0 derivative means don't change anything. Cosine of 0 is 1. Pretty simple. And then let's take the first derivative. That's negative sine x, right? See, this is 0, this is 1, like n, 0, 1, this is 0, okay? 2, negative cosine of x. Well, that's negative 1. 3, sine x. This is 0. 4, cosine x. This is 1. No. Stop here. Why? Because it's a pattern. Cos, negative sine, negative cos, sine, cos. It repeats. So, if we were to put this together, the series would repeat. So let's put this into a formula. Remember, let me write the formula right here. The sum of n goes to 0 to infinity, infinite amount of n's, of infinite amount of derivatives, add 0, right? Times, well, x minus 0 is just x, so let's just leave it at x, to the nth power, over n factorial. Okay, let's write out each term. Okay, so first value, so so this is actually g, so let's put this as g over here, just to make sure you guys don't get confused. So the first value will n is 0. Okay, so this 0 will both be 1, so that'll be fine. Okay, the 0th derivative of g of x at 0 is 1. So let's just, so g of x must be equal to 1 plus, okay, that's a 0. So I would put 0 here, but we all know that 0 times any number, 0 times spaghetti, 0 times pizza is 0. So we're going to skip that. Okay, so we have a minus over here this time. So minus, it's 1, so whatever. This is the second one, so x squared over 2 factorial plus, skip 3 because that's a 0. Then x to the 4th, because that's the 4th n, well, 4 factorial. Well, if this is x to the 0, x squared, x to the 4th, and it's alternating, we can probably fill in the rest. Minus x to the 6th over 6 factorial, plus x to the 8th over 8 factorial, so on, so on, so on. So if we were to put this into sigma notation, we would get this. Okay, so we're going to do sum first, n equals 0 to infinity. Okay, keep in mind, we're doing all the odd numbers, the derivative is 0. So we don't have to worry about all the odd ends. So all we have to worry about is the even ends. And the way to represent all even numbers using n going from 0, 1, 2, 3, 4 is just multiplying a 2. Because if n is 0, 1, 2, 3, 4, 2n is 0, 2, 4, 6, 8. Get the point. So this is going to be, well, keep in mind, it's alternating. So we don't have to worry about this g thing. So negative 1, alternating, right? So it starts out positive. So if we do to the n, right? Because if n is 0, negative 1 to the 0 is 1. That's right. So if n is 1, negative 1 to the 1 is negative 1. So that's right. 2 is 1. 3 is negative 1. 4 is 1. So that's how we represent alternating, is by raising negative 1 to the nth power when your n is going from 0 to infinity. Then we have x to the 2n, because we're only doing evens, divided by 2n factorial. See, so this is actually just all equal to cosine of x, right? This is equal to cosine of x, this is equal to cosine of x, but yeah. And obviously, if you're a comp sci nerd and you know about your for loops, this is really easy to use for loops to compute. So now you can compute cosine like that. So let's do the similar thing for e to the x. And obviously, you guys, in fact, you should pause the video and you should try it yourself. And what I'm gonna do is I'm gonna put this in 2 times speed, me trying to solve it in 2 times speed, and you just check yourself. So here we go. Okay, did you get it? Well, if you're still bombarded on why I got this, let me explain it to you. This is e to the x, and e to the x is that fancy function that differentiates to itself. So e to the x, e to the x, e to the x, e to the a, you get the point. Plug in the 0, you always get 1, 1, 1, 1, all the way down. So if you plug it in, this is always 1, so we don't have to worry about this term. So all you have to do is, there's no fancy parts of any n factorials getting cancelled out or any alternating, so it's literally just this if this is 1, so voila. This is equal to e to the x. Okay, well, hopefully this helps you, and yeah, I'll see you later.